make sure I didn't stop it, right? Okay, right. Feel free to do some Zooms or whatever else you need to, right? Alrighty, so here we are. I don't know about you guys, but if you're feeling like me today, then I was like, should I just cancel class just to, but like, no, then they've already woken up, and everything. So, no, but it's okay. We have just a couple of things that I wanted to kind of finish up here and just kind of work through you guys. So we will have a little bit of a shorter class today, I'm sure. Like as long as you guys get all the, look, if you guys get all the answers within the first 60 seconds, then the material I have will be done, and then you guys will just, so you guys can go hunt Geo instead, right? But anyway, so just a couple of things that I wanted to wrap up here at the end of chapter 17, just to bring a little bit of some thoughts to this idea of solubility that we had. And then on Monday, I'll talk to you a little bit more about some of the other kind of points I've been, let's say, processing. I've been going through the exams and starting to grade those, and we'll just talk to you a little bit more about that sometime next week when I've got a little bit more thoughts to put together, I guess, with that. So we'll get those back to you guys, and as I promised, I'll have your corrections are done. I'm just, going to hand you guys back that stuff at the same time. There's what it is. So we'll get all that stuff back to you guys next week. You're looking sad already, huh? No worries yet. No worries yet. It's all good. You guys will be just fine. All right. So, all right. I ran out. I have to go make some more. All right, got it. But it'll be okay. So yeah, and I guess then we'll get started with prayer, and then we'll take a look at some of these problems. But Lord, we just thank you. Lord, we just thank you for just the vision of yourself that you give us each day, Lord, and the small things that we see, and even the large things that we get to experience today. Lord, we know that your hand is in all of these things. And Lord, we just thank you. We thank you that you've given us eyes to see you just a little bit more each day, Lord. We pray that you just, take those scales away from our eyes, Lord. Just help us to see you in your hand in everything that we do, and in every step that we take, and the thoughts and our actions. Lord, just help us understand that it is for you and for your kingdom. And Lord, we just pray that that the talents and the gifts that you've given us can be used for your glory, Lord. Just give us those opportunities today, Lord, to show us what it is that you would have us do, Lord, and to speak clearly to our hearts. And so give us the courage when we hear your voice too, Lord. We just pray this in your name. Amen. All right. So we had wrapped up this idea of solubility. And I just wanted to give you guys a couple of examples here about some of the typical problems that come out of the solubility portion of the chapter. And then I wanted to draw your attention to something at the end of it here. So we'll work through a couple of problems. If I find my pen. Yep. Okay. Cool. So let's start with, calculate. I'm just pulling a couple examples from the textbook as all it is. The molar solubility. Silver carbonate. All right. Cool. Calculate the molar solubility of silver carbonate. Was that your green for St. Patrick's Day? Mm-hmm. Just put sticky notes all over your t-shirt. Just because it doesn't quite fit in with, we might come back to it at the end of the semester. Let's put it that way, right? But it's one of those, it doesn't quite fit in with the narrative, like how the next thing we're going to talk about is like free energy. So then that kind of builds off of equilibrium and these kind of things, so. No, it's not boring, it's environmental chemistry, exceedingly important. I know, but I'm being serious, like, you know, it's exceedingly important. And it's really, it's not so important in the sense of, necessarily, well, it's important in the sense of understanding how it fits into the modern conversations that we're having. You know, like everybody talks about global warming and all this kind of stuff, and there's where it'd be really important to have a good discussion with you guys so that when you're presented with data, you guys can draw your own conclusion, right? That's really the goal. Otherwise, I'm just telling you my opinion based off of the data. So. But like I said, we might talk about that a little bit later.
Don't we need some numbers?
Aha. Don't we need some numbers, right? So be careful. So when you're presented with a question like this, right, in this manner, there's a couple of important things that we need to figure out to begin with. First things first. Anytime we're dealing with solubility, right, pretty much we're going to need to find our KSP, right, our solubility constant, or the equilibrium for solubility product, right, KSP there. Now, where are we going to find something like that? In the book, right? In the appendix, through Google, right? You guys have access to all that stuff, right? So if we take a look, and I think it's Appendix D in your guys' textbook there is where the solubility products are, the KSPs. And if we look that up, oh, sorry, I skipped a step before we got that. Well, first thing, before we look up the KSP, what do we need to know about silver carbonate?
The chemical equation.
Concentrated.
Well, before that, we need to know what in the world the formula is, right? Because when you take a look at the appendix, right, it's not listed by name. It's listed by, you know, here's the formula for it, right? I think, if I remember correctly.
Carbonate just has a negative 1 charge, right?
Aha, so here we're again at the same point that I keep ending up making here, right? Carbonate is one of our polyatomic ions. CO3 with a 2- charge, one of the most important polyatomic ions, let's say modern contextually, especially here in Florida, right? If you guys have ever been around Florida, some of these national parks, right, they talk about the sinkholes that form, or you've seen in the news, right? It's because of carbonate and the stuff that's in the rain and acid rain and acidity and pH, eroding carbonate formation, and then you have a giant hole that forms in the ground, right? I know there's a park outside of Gainesville, Florida. It's called the Devil's Mill Hopper. It's a giant kind of sinkhole that opened up there, and you could walk all the way down to the bottom, and it's very underwhelming. It's impressive what happened, but at the bottom I thought I was kind of like, oh, okay, it's such a big hole, but it's a good walk in the park, all right? Anyway, right? But so modern, or aside from that issue here, right, we need to know what the actual formula is. You have to know how to convert names into formulas into names. It's very, very important when we're dealing with solubility and equilibrium in general, right? So silver always has a 1+ charge. This is one of our exceptions, right? Silver is in our transition metal block in the periodic table, and so normally we think of those as our variable, right? As our variable cationic charges. You guys remember talking about this variant and invariant charges, all this kind of stuff? Right, but silver is one of these exceptions. It's pretty much always going to have a +1 charge. Very, 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 very rarely read that as never in this class will we see it deviate from that. Okay, so silver always 1+. Now, so silver carbonate, Ag2, right? CO3 is what it is. Good. Why is it important to get that right?
Because that'll become the exponent of KSP.
Right. So when we break these apart, right, the concentration for silver is going to be twice that of the carbonate, based off of our stoichiometry here, right? Based off of our chemical formula. You guys with me on this one? Yeah, what's up?
Why is it just Ag2CO? Oh.
Yeah, sorry, it just kind of, yeah, it is, okay. You mean, why isn't it the right answer? Is that correct? No, you're absolutely right, yeah, that's just my handwriting. So So make sure you guys have the right formula before you guys start to approach this, otherwise it's gonna throw off your math with that too, right? So then if we go and look this up, our KSP is equal to, I got 8.2 times 10 to the negative 12, okay? So what does that tell you, right? Whenever, again, this is something I try to emphasize with you guys whenever we look at any Ks, right? Remember when I say, hey, look, weak acid, strong acid, look at the Ks, what do they tell you, yada, yada, yada. Same thing here. Right? I got a KSP of times 10 to the negative 12. What does that tell you?
It's not very soluble.
Not very soluble at all. And in fact, if you go look at the solubility rules that we discussed in the first semester, there's a rule that assesses carbonates, right? So you guys can go kind of match up and see how well that list holds up when we're doing some calculations here. Okay, so now we have the information we need to get started, right? We're asked to calculate the molar solubility. We have our KSP, we have our formula, so now we can start to put together the, let's say the expression, or start the, the equation for this. So remember, what we're dealing with here is when we take silver carbonate and we dissolve this into water, right? It's going to split up into, let me back out here for just a second. Let me do that, yep. 2 of our Ag 1 pluses, right? Plus CO3 2 minus. It's going to dissolve to some extent, not a big extent, right? Because the KSP is small, right? But still going to dissolve to some extent, right? So remember, our thought here is that for every one of these, I make 2 of these and 1 of those. Right? That's what our coefficients tell us there, right? But we don't know what the solubility is, right? So we don't know if it's 1 or 2 or 1, but we know that's our ratio of it. So remember, in essence, we can call it S or X, right? So if this is S, this has to be 2S, and this is S over here. Right? You guys with me on this? I think there was some confusion last time about where we get the 2 S's and why and all this kind of stuff. This is what I'm talking about here, right? For every one of these, I make 2 of those, right? So the concentration here has to be twice, right, of the other components that are there. But this is K, right? What's the concentration of a pure solid? Well, it's a constant. It doesn't change for us, right? So it's not part of our K expression. That's why we leave it out. You guys with me on this? So essentially we just ignore this part over here and we just deal with that part over here. Okay? So who cares about that stuff, right? So now we have KSP equals, right, the concentration of silver, right, squared CO3, 2 minus, okay? Do we have an expression for the concentration of silver? That's 2S, right? Do we have a concentration for the, expression for the concentration of carbon? It's S, right? Or 2X and X, whatever variable you guys want to put there, right? Good? So we have 2S squared times S, right, equals our KSP. So when we square this, right, it becomes 4S squared times S, which equals 4S cubed, which is equal to 8.2 times 10 to the minus 12. Remember, if you're multiplying things to powers, you add the powers together, right? Can you guys take it from there? Divide by 4 and take the cube root. Do all that, I got about 1.27 times 10 to the minus 4, right? Good? Yeah.
That's not too bad, but I'll still probably screw it up on the next exam.
That's right. Always aim for the stars.
What does that represent then? Because the one given concentration, is that how much?
Yeah.
I know that's how much will dissolve, but we don't have a much, so like what is that?
That's the question, right? Did everybody hear that question that he asked? Like, what in the world does this mean? Well, it means you get a 10 out of 10 on the question. That's always useful, right, if you get that answer. But what does it represent, right? Yeah, what's up?
How much will dissolve in an aqueous solution?
Well, this is the, right, this, remember this S, go back to our table that we have there, right? You're not wrong, right? Remember, this S represents the concentration of the components at equilibrium. Got it? This is just like the E part for your ice tables, when you guys were solving through all of those. That means if my concentration is above or below this, that tells us something. Okay? That is our concentration at equilibrium for the different parts of what S represents there for us. Got it? Now, of course, this is concentration, so it doesn't tell us about the solid, right? And this is a, I don't know if tricky is the right word here, right? But remember, these things can only come from that solid. So it tells us how soluble that molecule is, that ion, the ionic compound is. Is everybody catching me on this one? The only source I have for the silver and the carbonate comes from that solid. So the concentration has to come from that solid. So that S represents how soluble this thing is. Does that make sense?
So is it a concentration, RS?
Yeah. We're dealing with K, right? And this is all concentration-based Ks.
Okay.
Good? That's the thing, there's a couple of tricky parts in here. The first one was make sure you guys remember how to convert names to formulas, formulas to names, right? The second part is make sure you guys know where to get your K's, P values from. Right? The third one is make sure you guys understand the relationship between your coefficients and your exponents and all this kind of stuff, right? AKA write a balanced equation is what I'm saying, right? 2 silvers come from one of these silver carbonates. If you don't have that 2 there, it's going to throw off your number at the end, right? So double check your math. One more, all right. Or one similar, one more. Spare you guys the coming up with the formula and looking up the KSP here. So, what is the solubility of calcium phosphate?
She doesn't like the water. So she doesn't like the water.
No. There's something interesting to look at with your KSPs though. How does the charge of the ions relate to the solubilities, right? Phosphate's a 3 minus, carbonate's a 2 minus. Right? Think about which are always soluble ions. one of these, I make 3 of those and 2 of those, right? So here we have our 3s or our 3x, whichever one you guys want to use, right? We'll go crazy and use x this time. It's Friday, right? That's how we roll. Woo! Okay. So far, everything's still the same, right? Write out your expression for your KSP. Right, calcium 2 plus cubed, phosphate 3 minus squared. Then we have 3x cubed, 2x squared. Okay. And we got to do a little bit of math here, right? So 3 cubed is 27. So here we have 27x cubed times 4x squared, right? And that is 108 x to the 5th, right? So 27 times 4, 108, x cubed, x squared, x to the 5th, right? So just to kind of bring this up here, so 108 x to the 5th equals, what was it? 2 times 10 to the negative 29, right? I think that's what I got. Yeah. Right. Good. So you divide by 108. How do you deal with that x to the 5th though? I don't, my calculator doesn't have a 5th root function, right? Hmm? Well, that's one way, right?
Or you could raise it to the 1/5 power.
Right, so remember if you raise it to the fraction there, right? If you raise it to the 1/5, that's the same thing as taking the 5th root, right? So raising thing to the 1/2 is the same thing as the square root, raising to a 1/3, cubed, right, et cetera, et cetera, et cetera, right? Good? What you guys end up with? X equal to what?
I got 7.14 times 10 to the negative 7.
I got that as well.
Thank you.
Good. What does that tell us? X in this case represents, right, the concentration of the ions, right? Well, excuse me, let me back up here, sorry, I misspoke that. X represents the, right, how much of the calcium phosphate could be dissolved into water here, right? Because remember, where we're getting this from, right, if we, just for a minute, right, we would think of this as X there, right? That's how we base the 3 and the 2 for our concentrations from, right? If this question instead asked, what is the concentration of calcium, then what would we have to do? Take our X and do what? Multiply by 3. You guys with me on that one? So be careful about what the question's asking you to do. Okay, remember we just solved for X. What does X represent within the question or within the expression that we have here? You have a question?
So I'm assuming if that reactant, the solid, had a coefficient, then we would do all the other coefficients based on
Yeah,
that.
but that won't really happen, right? Because we're talking about one thing splitting apart, right? But yeah, if there was some issue like that, then we'd have to just go back and reassess what our X's are. Yeah, I don't know. Sorry.
I still don't understand why you're using like the 3 and the 2 twice.
Because we have to figure out concentration, right? For every one, right? Because we're setting the calcium phosphate as 1, and there's 3 calciums that come out of it, right? So the concentration is going to be 3 times that, is what it is.
Okay, then why do you then have to raise it to the 3rd power?
Because that's how we deal with equilibrium, right? The coefficients, right, in our balanced equation up there, right? The 3 calciums, that becomes our exponent.
Okay, so is the exponent always the same as the coefficient number in those?
Yeah,
Yeah.
yeah.
two different processes, like the KSP equation that you're writing out is using the same stoichiometric
Yeah.
process that we've been using forever. It's just that then when we go to find X, it's another new process, and that's where we're getting that number that we're then plugging in to the equation.
Remember, we have to, this is all concentration based first is what it is, right? I think we get so used to doing it in like the acid base stuff where everything's in a 1 to 1 to 1 to 1, right? But remember where your exponents go with this stuff. It's a good question. All right, let's see, which one do we want to do next?
The one that won't fry our brain.
We'll try this. So, question. Getting kind of more complex here, right? So does a precipitate form when I mix those two together, right? See what you guys can start to come up with. What's that? Well, the first question is, what do you need the KSPs of? Right? And then you would need something else also. No, we're not, no, that's for complex ion information. Yeah, we don't need that here. We're not forming, we're just saying does something precipitate, that's all. Yeah,
So we have to need two separate ones,
what do you mean?
two separate equating ice tables.
No, you're only end up needing one. So here, let's think about this real quick here. So what in the world is this question even asking? So we've got two beakers of a solution, right? We've got silver nitrate and we've got the sodium sulfate, right? And they give us a volume, they give us a volume and they give us a concentration, right? So a couple of questions should immediately kind of spring to mind. First of all, it might be, well, hey, is silver nitrate and sodium sulfate soluble?
Yes.
Well, we can assume that's a yes. How do we know that that's a yes?
Nitrate and sodium.
Right, that's one way, right? If we remember our solubility rules, nitrates and sodiums are always soluble. What's the other way that we know that those are soluble? Subtle. But as soon as you
Because if they're in aqueous solutions that we're adding together, then they have to be.
guys got it, right? I'm not gonna trick, I'm not tricking you. I told you we have a solution of these two things. So are they soluble? Yeah, right? So we know that sodium sulfate and the lead nitrate there are soluble. Got it? We can make that assumption. But now we gotta think back to, oh, there it is. We gotta think back to what we did in Gen Chem. If you remember in Gen Chem, when we asked these questions about precipitations, right? What we had to do was take the two things that we were mixing together, we had to break them apart, right, into their cations and anions, and then bring together the new cations and anions. So we broke this apart into lead, 2 plus 2 nitrates, right? 1 minus, plus 2 sulfates, 1 plus 1 sulfate, 2 minus. Good? Now what's going to come together? The lead and the nitrate started out together, so the lead's now going to go look for the next negative, which is sulfate, right? Nitrate is going to find the sodium, right? So we can bring those new ions together, right? So we make lead sulfate plus 2 sodium nitrates. Everybody with me on this?
Will that be an equilibrium or just an equation?
Yeah, well, everything's in equilibrium, right?
Right, but it's heavily product favored, you're telling
Well, we don't
us.
know yet. We don't know yet.
But you wrote in forward arrow.
I might be deceiving you as I'm prone
You
to
said you
do,
wouldn't-
right?
You said you wouldn't try to trick us.
That's a quite, so it's a good question, but so I'm not trying to trick you with this, right? I'm just writing the reaction, right? You guys with me? So now that we have this, right, we can assume, right? We can assume that these two are soluble because we start out with solutions of those, right? Fantastic. So what do we need to do? We need to figure out what's going to happen with those two over there. Got it? So we look up the KSPs, or we look up the solubility tables, right? The rule number 1 in the solubility is that anything with sodium and nitrate is going to be essentially infinitely soluble, right? So that's going to stay in solution. So I ran out of room, but that'll stay in solution. But if we look it up, see that lead sulfate is going to precipitate out. It's going to form a solid.
So that's all you want out of us for this question? You don't want like a mathematical explanation for it?
No, we'll come back with a mathematical explanation, right? Yeah.
So did you get that from our previous knowledge of solubility rules or from the KSP?
Both, right? One has to back up the other.
How would KSP reflect precipitate?
Right. Here, then that's the question. This is what you guys are asking here. Because why would I give you all these other numbers, right? Because when does a precipitant form? A precipitant forms, right, when the concentration of the ions is higher than what it is at equilibrium. Got it? So we need to check the instant we mix these two together, we need to check what the concentrations are for the lead and the sulfate. Everybody with me on this? So pay attention to what I'm telling you here, right? So we have these two beakers, we mix them together instantaneously, we need to see what the concentration is. So what are we calculating? We're not calculating K, because we don't know if it's at equilibrium. So what are we really calculating? Q. And then we compare Q to our Ks to see if a precipitant will form with these amounts that we're adding together. Okay? the assumption that we made when we're doing our solubility rules is that we added enough that something does precipitate, right? But we could just add enough together here that it's below the equilibrium concentration, and it's not gonna precipitate yet. Is everybody with me on that? This is the complexity that gets added, okay? So we need to calculate Q. Well, what's Q? Q is the same expression as K, right? So we just need to calculate what Q is, okay? Remember, just to bring this point here, right? So we will take this, the thing that we think might precipitate, right? Lead sulfate. Sorry, I keep doing that for some reason. Lead 2 plus sulfate 2 minus, right? Everything here is in a 1 to 1 to 1, right?
Yay, simplicity.
Okay. You guys with me on what we need to do from this point though?
Hopefully.
So what else, what other information do we need to look up in our textbook or whatever? The KSP for lead sulfate. I'll do that for you guys, so we're all on the same page. 6.3 times 10 to the negative 7, that's what it is, okay? Be careful, be very careful. Think about the numbers that you're using. But this is a good start, see where you guys can go from here, okay? While you guys are thinking, what's going on in this problem? We have two separate solutions that we're mixing together, right? Everybody with me on that, right? We're mixing these two together. What is Q or K an expression of? Units in concentrations. So if I'm mixing two volumes together, right? Remember, concentration is what? Moles per liters of solution. So if I mix two volumes, what changes? My liters of solution. You guys with me on that? So be careful. So we need to take this into our new concentrations when we mix these two together. Everybody following along with this, right? Similar to what we did with our titrations, right? We have to reassess what our total volume is after each incremental step, right? I'm trying to lose my pen along the way. Let's see here now. So now I need to convert everything into moles and then back into concentration. So my total volume, right? Yeah, so 0.5 liters, right? I'm mixing those two solutions together, right? So the 0.1 and the 0.4. Somebody made nice easy numbers for us to add here, right? Now, my starting information tells us that I have 0.1 liters of, I should put that in there since I'm doing math, right? 0.1 liters of 8 times 10 to the minus 3 moles per liter of our lead nitrate, right? So I start out with H times 10 to the minus 4 moles, right, of lead nitrate. Okay. Which for us is important to tell us what? Not necessarily moles of lead nitrate, but moles of lead. Everybody with me on this? So pay attention. This is another part where jerk professors might try and trick you. Okay? Think about, remember, we're mixing the initial stuff together, so pay attention to the stoichiometry and the formulas and all this kind of stuff that comes with it. Okay? In our case, it's all equivalent, right? That's how many moles of lead we have too. So we have 8 times 10 to the minus 4 moles of lead ion, right? And we have that in 0.5 liters. So that's 1.6, right? My handwriting is quickly degrading because I'm at the bottom of my screen. Let me make this legible. 1.6 times 10 to the minus 3 molar, right, of lead 2+, right? Everybody with me on what I'm doing here? I'm figuring out my new concentration of lead the instant I mix these two together. So I changed my volume, but it's based off of my initial concentrations, right? Yeah. Good? So guess what we have to do next? The same thing, but with sulfate, right? You guys set up that expression? So after the end of it, I got 4.0 times 10 to the minus 3 molar of sulfate. So I ran through the same math. You guys just changed the volumes and the initial concentrations, okay? All right, that's part one. Okay. It keeps going. So what do we have to do next? Now that we've got our concentrations at the instant, now we need to calculate our instantaneous Q, right? What's going on at that moment, right? So we're setting up our expression for Q. Right, remember Q is just equal to, let me pick a different color, right? Q is equal to the concentration of lead. Right, the instant it's mixed, the concentration of sulfate, the instant it is mixed. Right, so if I plug those together, 1.6 times 10 to the minus 3, 4.0 times 10 to the minus 3. So if I did that right, I got Q equal to 6.4 times 10 to the minus 6. So what? Remember the question was, will something precipitate? So the answer is a yes or no, right? Based off of what? Our comparison of Q to our KSP. Got it? Because we don't know if we're at equilibrium. Right? We mix two things together. We're at the beginning of our graphs that we had. We have to see if we're going to move towards equilibrium or are we already at equilibrium. So now it just becomes a visual exercise, right? So Q is equal to 6.4 times 10 to the minus 6. I'm just zooming out, right? Up here, right, 6.3 times 10 to the minus 7. What's bigger, Q or K? Q. So what does this tell us? Will something precipitate?
Yes.
Yes, right? Because if Q is bigger, that means we have more products. So it's going to precipitate out to get back to our lower concentration. Everybody with me on that? If Q is less than K, what does that mean for us in this instant?
No precipitant.
No precipitant, and we can dissolve more into solution. Got it? until we reach our K, and then no more can go into solution.
Wait, so based on that, nothing precipitates until Q is equal to K?
Mm-hmm.
But if something has an extremely low K, then that's not hard to do.
Sure, right, yeah, it's a relative scale, right? Something times 10 to the minus 7 isn't very soluble, right? But we can still dissolve something, is what it is, right? Question. What happens to solubility when you increase temperature?
Comes up.
It goes up.
Why?
Temperature changes K.
Got it? We're dealing with equilibrium, okay? So, what's the only thing that changes equilibrium? Changes in temperature. You guys with me on this? Is this starting to kind of all click together in some horrid way, right? It's too much, right? But you guys with me on this? So, K changes our equilibrium, and so then we'd have to find a new KSP at that temperature, right? Which is, there's no tables for that stuff, right? We'd have to give you some other information about, right? What's up?
And the KSP for the lead sulfate, you just got that from the table?
Correct, yeah. Yep. Good. Let me ask you another question here. So now we worked two, let's say, easier problems, and then we worked a fairly complex problem. How did we end up solving all of these problems? Well, yeah, but specifically, what did we end up doing? We figured out what? Concentrations at equilibrium, right? We ended up solving Ks for each one of these. You guys with me on this? So if you're stuck on one of these problems, what's probably a good place to try to work towards? Go ahead, everybody at once. Right? Figuring out your Ks, right? Set up an expression for K and do something with it. Right? And then step back and go, no, okay, right? And then figure out what in the world does it represent for the information that you have. This is the tricky part of chemistry. We make you guys do math, and then we make you do what? Think about it. Got it? That sounds awful. Why would anybody do this? I'm joking, it's fantastic. Right? I love it. You guys not convinced yet, but don't worry. I'll have you guys for organic chemistry. I'll change your minds, I promise. Okay? But you guys are with me on this? So this is the tricky part. When you guys are working these practice problems, when you guys are looking at the stuff in the book, it's not just a number. If you're just thinking about like, oh, thank goodness I got a number, you're missing the most important part. You have to convince yourself that that number means something. Okay? Otherwise, you're just working through some math and it's not going to stick with you. You have to think about what this stuff means. What are you physically doing when you're mixing these two things together? It's difficult because it's just words on a page, right? But if you're missing that important step of taking a step back and looking at what it is and what it means and what it represents, then you're going to be missing all these important things that go along with it. So take your time and think about the practice problems that you guys are working through, okay? You can work 50 practice problems, and if you don't think about what it means, it's not going to benefit you at all. Working 5 good problems where how much time did we spend on this problem, right?
About 45 minutes.
Right? What did I spend more time doing with you guys? Explaining it or doing the math? Do you guys get what I mean with it? It's not just because I like to hear myself talk. As soothing as my voice is, right? What do you, wait a minute. Right? But you guys get why? Because I'm trying to tell you, this is my thought process when I go through these. Ugh, peek into the brain of Dr. H, right? Why do I do it though? It's because otherwise I don't understand what I'm doing. And then I can't set up the math and it means nothing, okay? So start working on your inner monologue is what it is. Promise, promise, promise. It'll be so much helpful if you guys do that, okay? Good? All right, so we'll call it there for today. I'll see you guys on Monday. And we will pick up with chapter 19, right? Then chapter 18 is the environmental chemistry stuff. We might come back to that a little bit at the end of the semester there, but 19 is where we're going to be going, okay?
Thank you, Dad.
Of course.